Hello, everyone. Thank you. First of all, thank you for coming today to my presentation. So today I hope to teach you about embeddings, what they are, how they work, and how you can use them. If I've done my job right, I hope to make you just as excited by embeddings as I am. So to start off, we're going to go through some of the pre-2013 methods for embeddings and work our way to state-of-the-art neural networks. So, first of all, what are embeddings? Fundamentally, embeddings are a way to capture information and represent it on a computer. This information is typically language or images, but can really be anything. For the purposes of this talk, I'm just going to be covering language. So when we say we're going to embed a word, that means to take a word and embed it into a vector space where similar words are closer together. This, in essence, captures semantic meaning and turns it into a vector of numbers that we can then use computers with. So how can computers understand language? Well, maybe we can try and define a giant dictionary full of all the English words and their definitions. But that doesn't really capture any sort of semantic meaning. Well, maybe we can then order the dictionary so that similar words are closer together. But what happens when the word changes depending on the context? For example, if I'm talking about bugs, am I talking about bugs insects or bugs computer errors? Maybe then we could try and hard code all the different types of contexts, but I don't think any of us really want to be writing over a million if statements. So it turns out the solution to capturing word embeddings and capturing word meaning begins outside the world of computing and instead in the world of linguistics. John Rupert Firth proposed the idea that words with similar meanings will appear in similar contexts. This is called the distributional hypothesis and is best described by his 1957 quote, "You shall know a word by the company it keeps." The central idea here is that words with similar meanings will appear in similar contexts. This means that you can derive a word's meaning by the context in which it is used. This is the basis for the way modern computer science captures semantic meaning in modern natural language processing. So, prior to the advent and subsequent domination of neural networks algorithms in the early 2010s, natural language processing relied heavily on rule-based systems and symbolic systems, much like the ideas we played around in the slides before. But there's actually another class of methods that were called the statistical methods. Many of these statistical methods are based on word co-occurrence and bag-of-word approaches as a form of embedding words and text, respectively. So, for example, we can use the word co-occurrence matrices. So we can use the frequency of words within a context window of a certain word to create embeddings. A context window is just the words in front and behind the word that you're looking at, and can vary in length depending on the model you're using. So when you count all the times a word occurs within another word's context window, you get what is called a co-occurrence matrix. So this one, for example, along the top here, I've just taken a subset of the words, and likewise down the bottom, but in reality, you're going to get a matrix that's the same size as it is long as it is wide. So along the top, we have a subset, and this will often be hundreds, thousands to tens of thousands of words long, depending on how big your documents are. So the word digital, for example, has had computer, the word computer, occur 1,670 times within its context window, and the word data occur 1,683. This makes it very dissimilar to words like cherry and strawberry, which have had very few occurrences of those words, but are high in words like pie and sugar. If you just take 2 dimensions out of this matrix, you can actually use it to kind of plot the words. So if we just use the dimensions computer and data, we can see that the words digital and information are actually very close together. And oftentimes when we're measuring a sort of closeness with vectors, we're not using how far away the dots are, but instead we're measuring the distance of the angle between them. So the angle between these two words are very low. So this is called cosine similarity, and it'd be pretty high in this case. An adjacent concept to this is bag of words. To create document embeddings, we use a bag of words, which means we can encode our documents to be a count of all the words it contains. So if we have these three documents, this would be our vocabulary, which is just all the unique words in our documents, and these would be the word frequencies. What we are left with are document embeddings, and this is a useful way for comparing documents based on the words that occur within them, but it doesn't make any attempt to compare the documents based on the meaning of the words within the documents. So, both of these family of statistical methods use the frequency of occurrences in order to derive some notion of similarity. The idea here is that similar words will have a similar number of co-occurrences, and likewise similar documents will have a similar number of word frequencies. These methods produce large dimensions because often the size of the vocabulary is how long your dimensions are going to be. These methods also produce what are called sparse embeddings or sparse vectors because they mostly contain zeros because most words don't occur next to each other. So by the early 2010s, neural networks were experiencing a bit of a renaissance in computer science, driven by advances in compute power and neural networks demonstrating how good they are at classifying whether an image is a cat, dog, or a muffin. So, the introduction of Word2Vec in 2013 by Thomas Mikolov and his team at Google combined natural language processing and neural networks. Instead of just counting the word neighbors like we did in previous methods, we feed the neural network examples of words that are neighbors and examples of words that are not neighbors. And then we force it to predict which is which. For the predictions to be accurate, the neural network is forced to capture some sort of deeper contextual deeper semantic understanding of the words so that it can actually make accurate predictions when we force it to predict. So the training data for the Word2Vec model is nothing complex. All you need to do is process all your data to create a bunch of word pairs. You can do this by looking at the words that occur within the context window of a specific word and labeling them as neighbors. So for example, hard has a context window with the word implementation in it, and we'd want the neural network to predict that those two words are neighbors. We do the same thing for is until we get a list for that word. And then we iterate to the next word. So we go to 2, and we do the same thing for all the words in all of our documents until eventually we get a giant list of all the words and their neighbors. Equally as important is that you randomly sample words that don't occur together and label them as non-neighbors. If you don't do this, the neural network could get away with labeling everything as, or predicting everything as neighbors, and it would be 100% accurate. Before we move on to discuss more about the Word2Vec algorithm, we need to quickly do a bit of a primer on neural networks. So neural networks are structured in a way that they take data as input and transform it via its layers into a desired output. So for example, if you were to train a cat classifying neural network, the inputs would be all the pixel values of the image, and then the values would then be transformed through the layers into maybe a binary output that represents whether the image is a cat or not. So essentially, neural networks are really good at learning patterns, and much like a child learns, it needs to be exposed to examples and feedback to become good at recognizing something. Unlike a child, a neural network stores its learnings in matrices that are often referred to as its weights. So in this diagram here, these would be the neural network's weights. The weights are responsible for propagating the data from one set of layers to the next layer. And each time you show a neural network an example, it adjusts its weights to minimize its prediction errors, which then improves its ability to make correct predictions on unseen data. Just a bit of a clarification. This is a major simplification, but it should give you just enough intuition to work with. So to train a model using the word-to-vec algorithm, we use a neural network to predict the most likely context words for each word in our vocabulary. So the diagram we showed before, it's very similar to this neural network, except I've just blown up the weights and made them into squares for it to be easier for us to visualize. So the first set of weights in the word-to-vec algorithm is a V by N matrix, where each row corresponds to a word from the V-dimensional vocabulary. The N columns contain floating point numbers that are used to represent the word's meaning. They are typically around 300 columns for word-to-vec models, but there's no limit, and they may range between 50 to 1,000, where smaller dimensions are more efficient computationally, but they do tend to sacrifice their semantic resolution, much like you would when you limit the amount of pixels you can represent an image with. So these particular weights in the word-to-vec matrix are actually referred to as its embedding matrix. And as it's learning to maximize its prediction accuracy, the neural net is slowly nudging the numbers in there so that similar words have similar numbers. As you may have guessed, we're not actually interested in the predictive ability of the neural network, but rather the embedding matrix that is created as a byproduct of it. Once training is complete, the matrix is harvested, which is what we use for our word embeddings. The trained embedding matrix provides dense representations of words, which means every number in the word embedding is meaningful and contributes to its representation, unlike the sparse predecessors we just talked about. These dense embeddings contain really interesting properties that actually are, the best way to illustrate them, I think, is to compress your 300 dimensions down to 2, so you can see them on a graph. So if we look at the first property, for example, we can see that these embeddings are fantastic at capturing meaning. Similar words like fantastic, awesome, and amazing are all in the same location, whereas terrible, awful, and dreadful are all in their own group, and unrelated words like bug are all the way by themselves. The second thing that I find really interesting is the ability for embeddings to preserve semantic relationships, like tense. So here we can see flew is to flying, as ran is to running. And the cool thing is, no one trained the neural network to do this. Just by forcing it to predict its word neighbors, it was able to capture these relationships by itself. It also captures real-world information, so Canberra is to Australia, as Beijing is to China. And a consequence of these relationships that are captured is the ability to perform meaningful vector arithmetic. So if we take the embedding for Canberra and subtract the vector for Australia and add the vector for China, you get a vector that is approximately the same as the vector for Beijing. And to prove this, I've used the most similar function in the model I've been using, and I did the computation in there. And you can see the top 5 most similar vectors. You're getting Beijing right at the top, followed by China, Canberra, Chinese, and then a typo of Beijing. So up until this point, our embeddings have been static representations of words. Pre-2013, the statistical methods used static vectors that were long and sparse. They were long because every dimension literally represented the count of a specific word. Word2Vec, on the other hand, it uses the learned representations of words from a neural network, meaning that each dimension, while not directly interpretable, is used to represent the meaning of the words. This makes Word2Vec much more efficient and effective at capturing word meanings, because the dimensions end up being a lot smaller. But it's not perfect. There's a problem. Word2Vec produces static word embeddings. Therefore, words with multiple meanings end up being encoded as some sort of awkward average between all the context in which it appears. So for example, this is a general model, and so you can see the word bug is stuck between insect and error/glitch. So this model was probably trained on general information, but if you trained your model on, say, biological text, you would expect to see bug right over by the word insect. And likewise, computer science textbooks or so on, you'd expect to see bug right next to all the error and glitch sort of words. So what's clear is that for the best embedding of a word, you really need to have an embedding for each context that it can appear in. Enter BERT in 2018 by Jacob Devlin and colleagues at Google, which BERT produces dynamic embeddings, making them much more effective at capturing meaning. BERT uses a deep neural network based on the transformer architecture. And deep in this context literally just means that it has more layers, unlike the Word2Vec one, unlike the Word2Vec neural network, which just had one. So a bit of a tangent, and I don't expect you to take all this in, but this is what the transformer architecture looks like. On the left, you have the encoder, and on the right, you have the decoder. So the transformer architecture is foundational to generative models like ChatGPT-4 and representative models like BERT. BERT uses the encoder part of the transformer, which takes words and outputs embeddings. GPT, on the other hand, GPT-4, utilizes the decoder side, which takes embeddings and outputs words. Both the encoder and the decoder use what is called an attention mechanism, which allows them to focus on words more important to the context of the word than generic words like is, the, and. So this allows the encoder to create high-quality dynamic embeddings. This transformer architecture is behind the recent explosion in AI capabilities, and it's quite literally in their names. So ChatGPT-4, or GPT-4, stands for Generative Pre-trained Transformer 4. BERT, on the other hand, stands for Bidirectional Encoder Representations from Transformers. So BERT's a bit different, but it's also much the same. So BERT trains its equivalent to Word2Vec's matrices. BERT trains its equivalent to the Word2Vec embedding matrix by predicting missing words in a sentence. So explicit is better than implicit. It should predict better if we blank out the word better. And likewise, sequences of words like my dog is cute, he likes playing. We would want to force the model to predict that those are sequential. Because BERT produces contextual word embeddings, it takes sentences as inputs rather than single words, and then produces an embedding for each word in the sentence. Rather than harvesting the embedding matrix, like we did with Word2Vec, we keep the neural net intact so that we can continue to produce dynamic word embeddings. So now that we have context-sensitive word embedding models, given a word, a model will produce a vector that is specific to the word and its context. But what if we want to understand and embed sentences, paragraphs, or even entire documents? Well, it turns out the easiest way to do this is just to average all of the output word embeddings that our BERT model gave us. And this will give you a single vector that represents the entire meaning of your text. The reason we can't use models like Word2Vec to do this is because the word embeddings there are static and do not change depending on the context. So sentences like the cat chased the dog and the dog chased the cat would be encoded identically, despite the sentences having different meaning. A bit more on this. So static embeddings produce the same vectors for a word, regardless of the context it's used in. So my code has a bug, there's a bug in my soup, would produce the same word embedding, regardless of their context. Whereas a model like BERT would produce vectors for a word that are then modified by the presence of the neighboring words. So in this case, the role of, this is in BERT, this is the role of the attention mechanism, which selectively modifies the vector based on the relevance of surrounding words. For example, my code has a bug. The presence of the word code would be highly relevant to the context of the word bug, and therefore the embedding for the word bug would be modified so that it's closer to the word code. Likewise for there's a bug in my soup. And as you can see, the context on these words, BERT is using the context on both sides of the word. This is where it gets this is why it's called bidirectional. So before we move on to a quick demo, a quick recap on the methods we've discussed. Pre-2013, methods use static and sparse vectors to represent words, whereas Word2Vec algorithms use static but dense embeddings. This shift away towards dense embeddings hugely popularized the method of embedding words, and it became the go-to method until BERT was released in 2018 which provides dynamic, densely represented word vectors. But that doesn't mean word2vec can't still be used, and it often still is, since it's a lot more efficient. But it's not used where context is highly important to what you're wanting to do. So we're going to do a quick demo using the descriptions of the PyCon presentations to see which ones are most similar. We will use the library called Sentence Transformers, or SBERT, which provides great sentence embedding models trained using BERT. The first thing we're going to do is we're going to load in all the PyCon session titles and their descriptions, and we're also going to load a sentence transformer model and a cross-encoder model. And I'll tell more about the cross-encoder model later. So using the sentence transformer model, we calculate all of the sentence embeddings for all of our descriptions, all in one line of code. And then, like we talked about before, we can compress these embeddings into just 2 dimensions, and we can plot them. So this plot is pretty cool. There's not really any strong clusters, except for maybe the top left. We have all the education and teaching-related speeches, and in the top right we have all the Django and database-related speeches. But in the middle, yes, there is clusters there, but they're not very strong, and which probably goes to show that the PyCon team did a great job at choosing a very diverse set of topics. So let's say we want to find the most similar speeches to the speech Teaching Digital Technologies in Australian Schools for Python and the Kookaburra. So we get the index for it here, and then we now use PyTorch to compare the distance between, this is using cosine similarity, we compare the distance between the target embedding and all of the other embeddings for the speeches, and we want to find the top 10 closest embeddings to our target. So this is just like before when we had 2-dimensional angles. Now we have 300-dimensional angles, and we're calculating which ones are closer. So under the hood, it looks a bit like this, where we take in 2 embeddings, and we put them through a cosine similarity function, and that will return a number from -1 to 1, where -1 means that the embeddings are completely in opposite directions, and 1 means that they're in the same direction, or they're parallel. It seems to have done a pretty good job, because these speeches are all mostly related to education and teaching and all that sort of stuff, and schools. But one thing we've noticed is MicroPython, I don't think, is specifically about education in schools. So we can probably do a bit better here, and that's where the cross-encoder comes in. So using just the top 10 speeches, we compare our target speech description with, one at a time, with the top 10 speech descriptions. What this looks like is, this is what the cross-encoder is for, and it's also a BERT model, but instead of producing word embeddings, it's been optimized to produce a score, representing the similarity of its inputs. It does this by comparing each of the embeddings at a word level, rather than measuring the distance between the averaged word embedding of the model prior. This makes it much more precise in judging what text is similar. However, it's extremely less efficient, and that's why it's often done as a second step to kind of re-rank the results that the first step did, which is much more efficient. And it saves you from re-ranking a much larger set of documents. So if we go to these results, we can see that, for example, MicroPython has been re-ranked all the way down to the bottom, which goes to show that probably wasn't related to education. So I've actually got a live web app version of this, which will let you select your speech and see the most similar speeches, and I'll make that available right at the end. So embeddings can be used for a whole range of tasks, and I want to just go through a few more cool applications. This one's probably my favorite. You can actually see how the meaning of words have changed throughout time. So if you were to train like a word2vec model on documents from, say, the 1850s, you'd see that the word broadcast is used in a context that's very similar to farming and sowing seeds and broadcasting all the seeds. Down to the 1900s, broadcast becomes about newspapers. Down to the 1990s, broadcast quickly becomes about television, radio, and even the BBC. Another one that I find very cool is awful. In the 1850s, awful wasn't a good word, full of awe, amazing, majestic. Down to the 1900s and 1990s, awful very quickly becomes a negative word, meaning terrible or horrible. Another application is visualizing embeddings. I know I've spoken about this before, but it's actually really, really good for exploratory data analysis. And if the graph you're using is interactive, you can get a quick idea of what makes up all the clusters and get a real understanding of your data if you haven't seen it before. So in this example, you can see that the non-fiction genre of books are on the complete opposite side of the science fiction, which intuitively makes sense. The final application, or not the final one, but one of the bigger ones is vector databases. So vector databases essentially store all the vectors for your embeddings, which allow you to query them using embeddings as well. So for example, if you wanted to make a document search, you could then embed your query and find the most similar documents to your query. So this is actually used, as far as I'm aware, in Google and Yahoo searches as well, for sort of more of a semantic understanding of what you're Googling. And a common use case in modern applications is generative LLMs. So if you hook, your generative LLM generally isn't going to be trained on your data. So to give it access to data that's it's not been trained on, you can simply input the user's prompt into the vector database, retrieve the most relevant chunks of text or documents, and then append those to your prompt, and then feed the prompt and the relevant chunks into your LLM, and that'll then produce relevant information. And that's actually called retrieval augmented generation. And I believe there's a presentation or a workshop on that this Monday, so that'd be good. So that's really good for chatbots. Another way you can do it is you can optimize your sentence embedding models to kind of fit your definition of similarity. So out of the box, this model is doing what it should be. All the product descriptions are close together. But if you then fine-tune it, you can fine-tune it to be, for example, putting negative and positive sentiment closer together. So that's all the applications I've brought up today, but it really is up to your imagination with the embeddings. So as promised, here's a QR code, or a link if you prefer links, to the interactive demo. I haven't tested it really on anyone except myself, so we'll see how it goes. But there's probably no time for questions, but any questions, please feel free to come up and see me outside. Thank you.